So I invite Ahmed Almheiri from the Institute of Advanced Studies in Princeton. He will talk about the entanglement wedge of the couplings. So Ahmed, can you please share your screen?
So I actually decided last minute to change the topic of my talk.
Okay.
So instead, I'm going to be talking about comments on the final state proposal and the gravitational path integral. Can you guys see my slides? And can you hear me? Everything's fine?
I can hear you.
Yeah.
Okay.
Yeah.
Hi, Maddie. Been a while. How much time do I have for the talk? Speaking time?
You have 25 minutes and 5 minutes for talk.
Okay,
So
thank you so much.
Now it's 7:15. It's 7:15
Okay,
here in India.
All right. Okay, thanks a lot for the invitation to speak at this wonderful conference. I obviously couldn't attend all the talks, but I'll make an effort to watch them on YouTube later. So I'm going to be talking about a somewhat new perspective on an old idea on the final state proposal based on lessons that we learned from the gravity path integral. So this talk is a little bit about the information paradox. So let's review that. In the semi-classical approximation, let me just move this video. Okay, so in the semi-classical approximation, we know that the entanglement entropy between the black hole and the Hawking radiation grows monotonically because the radiation outside is entangled with its partners behind the horizon. Schematically, I'm going to describe the situation with, well, this picture and this quantum state for the radiation. This is supposed to represent some maximally entangled state between R tilde. Tilde will often mean particles behind the horizon, and R outside the horizon, and they're entangled, and the total dimension of the Hawking radiation Hilbert space is D. And this state comes about due to vacuum entanglement of the quantum field theory on top of this gravitational background, the black hole background. The state on a Cauchy slice at late times looks something like this. Here's this red, on this red slice, we have the total global state psi. It describes the matter which formed, or the star which formed the black hole in some state I, tensor product with the state of the Hawking radiation. If you're a purely outside observer, the state would appear from your perspective to evolve from a pure state of the infalling matter to a mixed state of the subsystem R, and hence information has been lost. The pure state I goes to a mixed state rho R, which for our purposes can be thought of as just the identity matrix. You can diagnose this the purity of the state by computing something called the purity, which is also called the second Renyi entropy, which is trace of rho squared of the system you're interested in. And in this particular state, because R is maximally entangled with R tilde, you get 1 over D, which is not equal to 1. If the state was pure, you would get 1. So that's the information paradox, but this talk is also about the firewall paradox. So let's review that as well. If you suppose that there's no information loss, then the entropy of the Hawking radiation must start to decrease after the page time. So we know that in order to have unitary evolution, the entropy of the Hawking radiation should go up and then come back down. It's always going to be bounded by Hawking's answer, the von Neumann entropy of the radiation, and the coarse grain entropy of the black hole, the area of the horizon over 4G. The statement here is that after the page time, or the additional constraint that comes from this unitarity condition, or that information is not lost, is that the outgoing Hawking modes after the page time have to be entangled with the old radiation far away. Or sometimes this old radiation is called the early radiation. Basically, whenever new modes come out, they have to purify the Hawking cloud far away. However, this seems to conflict with something else that we want, namely, in order to have a smooth horizon, vacuum near the horizon, we know that the outgoing mode has to be entangled only with the interior partner. Sometimes I will call this the no drama condition. So the conflict in the firewall paradox is that you need the late outgoing mode. It seems like it has to be entangled with two different systems. So these two requirements are contradictory due to monogamy of entanglement, as shown by in a bunch of works in the early 2000s. Well, in the early 2000s and also in 2012. The upshot of my work with Morov, Polchinski, and Sully was that a single infalling observer can potentially witness this contradictory state. If you have an infalling observer, like suppose you assume that you want everything, you want both vacuum at the horizon and unitarity. We know that that's an impossible quantum state, and what we showed is that an infalling observer, in principle, would be able to witness this impossible quantum state, and hence it's really a paradox. So, all right, so that's this picture here, and our suggestion was that perhaps one should replace the horizon with a firewall, and some other proposal was that maybe you should. Well, one way to get around this paradox is to instead impose some non-local encoding of the interior as part or as a subsystem of the outside radiation. I will talk more about this later. So this is the outline for the talk. I'll first discuss this old proposal of Horowitz and Maldacena on the final state. Then I'll discuss some problems that were pointed out of the final state. I'll propose a fix, and I'll motivate that from the gravity path article. Okay, so the point is that in order to quote unquote solve the information paradox, we need a mechanism that would move the information from the inside to the outside. What Horowitz and Maldacena pointed out was that this is doable via post-selection, where you simply declare that the state of the singularity is predetermined. It projects on the quantum state that evolves into it. So the rationale behind the proposal is that we like to think of the initial singularity that the Big Bang singularity that gave rise to the universe, if it's actually there, that it has some initial state. It comes with an initial state. And so why can't future singularities also come with a final state? And now the idea is the following. So the idea is that here's the picture of an evaporating black hole. You declare that there's some Bra vector on the singularity, which acts on everything that falls into it. And the state is a non-normalized state. There's some factor D, and it's a maximally entangled state between the infalling interior Hawking modes and the matter that fell in. Up to a unitary that acts on the matter. Okay, so that's the upshot. That the singularity projects the matter and the interior Hawking particles into a maximally entangled state. Let's see how this gives a channel for the information to come out. So you can see this most clearly by representing this space-time with a projection in terms of a quantum circuit. Here, this line here represents the infalling state of the matter in some state I. The the state phi d here of r tilde r represents the entanglement between the interior and exterior Hawking modes. Now the additional ingredient is that we impose a final state that projects on the subsystem M, including r tilde. And it's a maximally entangled state, as I described, up to a unitary on one of the legs. And so what this does is that just from the quantum circuit perspective, this gives you a channel for the information I to go through the circuit and appear in R. This unitary S that we acted here ultimately ends, it appears in the state of R as S acting on I. So this S should be thought of as the S matrix of the black hole. So this entire circuit can be collapsed into this equation down here that you end up with a pure state of the Hawking radiation if you post-select, and S is the S matrix as I described. Okay, so the upshot is that the state I of M evolves to the projected global state psi, which is a pure state of R. To analyze this proposal more, we need to consider a slightly modified setup where you take the matter that formed the black hole to also be maximally entangled with some outside reference. Okay. So imagine instead of collapsing a star in a pure state, you collapse a star in some mixed state that's entangled with something else. I'm going to write that state like this. Okay. So the global state now, I'm sort of I'm just considering some arbitrary decomposition of the state on this slice. I'm going to separate out some a qubit's worth of sort of maximally entangled pair across the horizon, B tilde B, and also the remaining everything else, the remaining radiation, and also the matter that formed the black hole into some entangled state R tilde R. Okay. Now, in order to have unitarity here, there's a condition that one needs to impose on the final state. The condition is that if you take the final state and you trace out R tilde, then the remaining density matrix of B tilde has to be the identity. What this essentially just means is that there's an isometry from B tilde to R tilde. Okay? So the state on F, that's one way to say it, that there's an isometry from B tilde to R tilde. Another way to say it is that in the final state, B tilde is maximally entangled with R tilde. Okay, as in the density matrix of B tilde is the identity. Again, it's not normalized perfectly. Well, it's just not normalized. The upshot again is that this, if you impose this condition, then this guarantees that B is going to be maximally entangled with R after you project to the final state. So again, you end up with a pure state of the exterior. B and R are in a pure state. Now we can ask, how does the final state, or what does the final state predict for the AMPS experiment? In order to answer this question, we first need to define the measurement operators. So let me first define the no drama operator, the measurement which checks, or in this case confirms, that B tilde and B are in the appropriate maximally entangled state. Okay, so this would be the measurement that checks that the horizon is smooth. There's another measurement that you can do which checks unitarity, namely that that BR are in a pure state, and also not any pure state, but the pure state that was prepared using the final state projection. Okay, so this is a measurement purely on the outside that checks that the Hawking radiation, that the entire cloud of radiation is in the correct pure state. Now, we're trying to define, we want to define probability. So, but in a modified, in some sense, in a modified, in a modification of quantum mechanics. The way you define probability here is you take the state psi, you project onto the measurement result that you want, and then you project to the final state, and then you take the square of that. Okay? So that gives you the probability of finding the measurement result associated to a given projection. So usually in regular quantum mechanics, this F would not be there. But here we're doing post-selected quantum mechanics, so the rules are slightly different. Let's compute the probability of there not being any, of there being no drama. Okay? So if you look at so this is the probability of finding them B tilde and B are in the appropriate final state, or in the appropriate entangled state. So if you focus on this diagram here at the bottom first, this is, if you ignore this blue square, then this is the state that you, well, it's the state of the radiation, or rather the state of the system, given the final state projection. And now what we're doing is that we're inserting into the quantum circuit the projection. Okay, so this now describes a quantum circuit where a measurement has been done, and you have to square it to get the probability. So that's this other that's the top half of the diagram. Now we can evaluate this diagram using the condition that we talked about before that ensured that you had an isometry from B tilde to R tilde. So that's this condition here, and you get 1. Okay, so this is the diagram that shows if you keep track of all the factors, count the number of loops, and so on, you get 1. Okay, so the horizon, the upshot is that the final state gives you the horizon. It gives you a smooth horizon with probability 1. You can then ask about a different question. You say, well, what's the probability of finding unitarity? Namely, that the outside state is in the correct pure state. Again, all you have to do is you have to insert these projections, and then use the properties of the final state. And this circuit diagram becomes again a bunch of loops. You count all the factors, you get 1 again. So awesome. So the evolution is unitary also with probability 1. But so far we talked about each measurement by itself. But recall that the AMPS experiment is about a single observer that does 2 different measurements. For that, we need to consider the probability of finding that B and R are in the appropriate pure state, and that B tilde and B are also in the appropriate pure state, in this order. So you first check that the outside, you have an infalling observer. This observer is falling in from the outside. They first check that the outside is in the right state, and then they check that the horizon is in the right state. Just by causality, this is the right order. So again, you put in the circuit, this means you first do the outside measurement, and then you do the inside measurement. You evaluate this circuit, and you get 1/2⁴. Okay, so you don't get 1 anymore. And this is weird. So to recap, the probability of the blue measurement is 1, the probability of the red measurement is 1 individually, but if you perform both experiments in this order, then you get 1/2⁴. This is acausal. The statistics of the unitarity measurement seems to depend on whether in the future you're going to check or you're going to perform the no drama measurement. And that's simply crazy. Let's take a closer look at the unitarity measurement. There's something funny about it. So that's given by this expression here. So right now I'm ignoring the no drama measurement. If you write this, well, the projection 𝝅 is given by this red box. The thing to note is that this state has two final state projections. One, which was originally defined, this F here, and one from the ket of the measurement operator. And so what seems to be what we seem to have is that we seem to have two different black hole interiors. There's the R tilde B tilde black hole interior, which was associated to the original final state. But then there's an R tilde prime and a B tilde prime, which are introduced by the operator. And so the question is, which of these is the true black hole interior? The answer to this depends on whether one considers the interior as a subsystem of the outside or not. In the following sense, if you were to take it to be on the outside as part of the outside, then if you do a measurement, a projective measurement on the outside, you should also project out the inside. Essentially, the proposal is that this circuit here should instead be drawn in this way. You have some state, and once you do a measurement, you completely project out that state, and what you're left with is the new ket that you what you're left with is the ket from the projection operator. This is familiar from standard quantum mechanics. If you have some state chi, now you want to measure if the state chi is in the state chi, you act at this projection chi. The new state is given by the ket of the projection operator. This is how standard quantum mechanics works. In some sense, whenever you do any measurement, you completely destroy the system that you have and you create a new system. You can think of it like that. And the idea is that in this setting, when you do a measurement on the radiation outside, you remove the old black hole interior is removed, and you create a new black hole interior. And this reinterpretation actually fixes this acausality problem. And the APS experiment now succeeds with probability 1. So here's a circuit diagram of what I'm saying. In that, so you start with the state of the black hole, then you do the BR measurement. That's this thing here. But after doing the BR measurement, you've introduced a new interior. And hence, when you do the B tilde B measurement, that has to be performed inside the new interior, not in the old interior here, which is way in the past in some sense. Okay. And if you do this, you get 1. So the probability of first checking the BR are in the appropriate pure state, and then checking that the horizon of the newly created black hole is in the pure state, then you get 1. Okay. In some sense, the problem that was found before by Basu and Stanford was that from the circuit perspective, they were trying to reach, after doing this red measurement, they were going backwards in time in the circuit picture, and that's the source of the acausality. The remainder of this talk will be about justifying this picture from recent results of using the gravity path integral and the page that reproduce the page curve and so on and so forth. So let me quickly recap that. So there have been recent insights from the gravity path integral regarding quantum entanglement in the theory of gravity. And so let's analyze this using a simple gravitational model that has aspects sort of similar to the final state. Let's consider closed universe states with particles that are prepared using the gravity path integral. I think something like this was considered in the paper of Pennington et al. So the picture here is that you have some Euclidean boundary, Euclidean ADS boundary, where you insert some states I and A, some particles, say, and at some point there are end-of-the-world branes that fall in from the boundary. This is just a way of preparing a closed universe. So I will call the state prepared, the state that the path integral prepares using this prescription as psi IA, C for closed universe. Now imagine introducing a reference system R, which you entangle with one of the particles, let's say the purple one, and let's say that the dimension is of this purple particle is large, and so then we have some entangled state like this. Naively, it looks like there is non-zero entanglement between the reference and the closed universe, right? So this purple particle is naively entangled with R. So I will demonstrate two things, the first is that R is secretly in a pure state, and that the operators on R can affect the state of the closed universe. The upshot is that operations on R, the way that they affect the closed universe is that they project out the closed universe, and they create a new closed universe with a new excitation in it. Let's first talk about the entropy. Suppose we compute the density matrix of R. So naively, what you do is, you just trace out the closed universe, so you get a picture like this. And actually, this picture would give you a mixed state for R. A more careful definition is the following, where essentially the prescription is to not fill in gravity unless you're computing a number, like the traces and so on. So when we talk about a density matrix, you should not fill in gravity yet. The norm of the state is just trace of rho. So now we're computing a trace. So we connect the outside indices of R, and then we fill in gravity. There's this, what I'm going to call the disk configuration. And this disk gives you a factor of the partition function Z, which cancels with the normalization, and you get 1. And there's a factor of D coming from this loop. You can then you can check whether the state is pure or not by computing the purity, which is the second Renyi entropy, trace rho squared. And what you find so you set it up in this way, and then you fill in the gravity. And what you find is that there's a way of filling in the gravity that gives you the original answer squared, okay, plus corrections. And we just said that the original answer is 1, so this is 1 plus 1 over D. So R is approximately pure for large D, as required. For the experts, this is actually exactly pure. This 1 over D is not there, in the sense that trace rho squared is equal to trace rho all squared. If this was cryptic for those unfamiliar with this, maybe we can talk about it later. It's not that important for the talk. Okay, so the last thing is the fact that the closed universe should be thought of as a subsystem of R. This can be demonstrated by finding operators on R that modify the state of the closed universe. This is related to this PETS map discussion of the paper of Pennington et al. The claim is that the following operator, so far this is trivial. The following operator, OR, it takes a closed universe of state A to a closed universe in state B. So let's define this operator, and one can check that the way that you check that this does what I claim it does is by computing its overlap, or rather its matrix element between a state of the universe with a particle in state A and one with a particle in state B. So and show that it's equal to 1. And so this picture here is given by this picture. And these are color coded to show what corresponds to what. And again, if you take this overlap, you get 1 plus 1 over d. Okay? So you get the same, it's 1 to very good approximation when d is very large. The upshot here is that when you act with OBA on the state psi, the way that it gives you a new closed universe with the state B is that you project out the closed universe in the state A, and what remains is the closed universe in the state B that comes from the ket of the operator. Okay, so the old closed universe gets projected out and a new one is created. Let me give one more very quick example, which comes from the evaporating black hole setting. This again is going to be schematic. So here's a picture of an evaporating black hole, which has some particle in the state A that falls into the island. OBA, the operator on the radiation. So here's an operator on the radiation. It acts, these I, J matrix elements act on the radiation subsystem. And the claim is that this takes the black hole from the state A to a black hole in the state B. And the way it works is the following. When you act with ORBA on state psi, so here, this is the operator and this is the state. It takes, you construct a new space-time that is composed of segments of the old space-time and also of the operator. So the action, so this operator acts on the radiation. So that's, well, the way it acts is that this pink region projects out the pink region of R, and it gives you a new radiation segment. The green segment of the operator projects out the island, the inside of the black hole, and the new interior comes from the operator. And the portion in the middle, because the operator doesn't act there, is retained from the old black hole. So you have this is your new space-time composed of new segments and an old segment. So that's pretty much everything I had. So let me just quickly review. So I reviewed the final state proposal and also talked about the criticism where it leads to these paradoxical results, this acausality. I motivated a fix of the final state, which takes into account sort of the intuition that the inside of the black hole is secretly a subsystem of the radiation, and that the interior can be get swapped with a new interior when you act on the radiation. And I motivated these, or rather motivated this intuition based on some concrete results from the gravity path integral that demonstrate that operations on the radiation influence the interior. That's all I had. Thank you very much.
Thank you, Ahmed, for a very nice talk. Are there questions? At least I didn't see anything here, but if anyone has question, please ask. Well, if not, then please thank Ahmed again.
Yes, I have a question. I have a question.
You have? Okay,
Yes,
okay, please. Yeah.
Yes, sir. In the AMS experiment, was entangled black holes considered?
You can apply the AMPS argument to entangled black holes, yes.
So if you have entangled black holes which are close enough, can the Hawking radiation from one have any kind of effect to the interior of the other, and hence the order in which we did the experiment, it might change the interior?
Sorry. I think I misunderstood your question. So entangled black holes, like you mean like a wormhole? Is that what you mean?
Yes.
Yeah. So that case is an example where the let me see. So I would say that that's the simplest example where the quote unquote interior being part of the radiation is well, it's an example of that. So when you have entangled black holes, like a wormhole, there's no firewall, as you know.
Recording in progress.
I guess what I'm saying is that so there's some echo. Can you guys hear me?
Yeah, Ahmed, yeah, we can hear you. Swapna, I think there's some echo. Are you logged in from two devices, or somebody is probably?
Yeah, seems to be some.
It's probably better now.
Yeah. So
okay,
Can you hear me?
I can hear.
Recording in progress.
No, it's back.
It's okay. Ahmed, you could go on with your answer. Sorry.
I was going to ask the previous the person that asked the question to maybe repeat the question. Maybe I strayed a bit too far.
Okay, sir.
Deepan, you can please go ahead and.
Yes. Yes. If we have two entangled black holes or a wormhole which is traversable, in that case, can the Hawking radiation of one be entering the other, and hence will that change something and hence will that also change the black hole interior or the singularity or the final state projection which we have taken?
I'm not entirely sure, but I would, if I was to make a guess, I would say no.
So in that case, also the AMPS thing will work, and the AMPS experiment will work, and the order will remain the same for the AMPS for the measurement in the circuit and the final state and the final projective black hole interior which we took.
I think the quick answer is yes, as in like in the sense that things the final state applying the final state proposal there with the fix that I proposed would continue to give consistent results, and there would not be a firewall. I think I hope that answered the question.
Okay, thank you, sir.
Okay, Gautam, please go ahead.
Thank you. Hi, Ahmed.
Hi.
Thank you for a nice talk. Yeah. I just had a small point, some curiosity actually, that your model sort of states that there'll be a projection, there'll be a final state projection, right? Is this projection unique when you make a measurement on the radiation system?
Yeah. So this projection, as I said before, that it has in it the details of the S matrix of the black hole. It provides the S matrix, and hence the details of the final state should ultimately be fixed by the theory that you have. So it's not a choice that we make. It's supposed to be part of the full UV complete theory that describes black holes. And no one up until now, I mean, we don't have that much information about, well, if that, there are no concrete proposals for what the final state is yet.
Okay, thank you.
Karan, please go ahead.
Yeah, I just wanted some clarification perhaps on the filling in the gravity afterwards part, which was there on the trace rho squared slide, I guess, the part where you were giving the prescription. So is that just a standard gravity path integral that we're performing here, or I mean, subject to certain boundary conditions, or is there anything more to this?
No, that's it. So you set up the calculation in this way. You say you have some boundaries, and then you impose some boundary conditions, And then now you allow for all gravity configurations that satisfy the boundary conditions.
Okay, so it's just the subjecting of boundary conditions. That's nothing else.
Correct.
Okay, thank you.
Somdat, please go ahead.
I have a question. Like, I have always wondered, like, how can a quantum state, a pure state which has to be a quantum state, how can it gravitate unless it collapses to a classical state or a classical configuration? How can such a thing gravitate? And if it collapses to a classical state, then the information is lost in any case, right?
I don't know what you mean by collapses into a classical state.
So for instance, if you have a quantum state, if you have a quantum field theoretic state, right?
Mhm.
It would have to it would have to collapse to some classical state before it can gravitate, because unless it collapses to some classical state in a specific space-time, it can't gravitate with the gravity in that space-time.
Why, I don't see why not. As in, I mean, I'm worried. I don't want to get into interpretations of quantum mechanics, but I mean, in our world, I believe everything is quantum, and there's some quantum state that describes me and the Earth, and I still feel its gravity. So I don't see how the gravitational force would not be there in a quantum description of the system.